Reflector antennas, parabolic reflectors, part 2, series on antennas and wave propagation, lecture number 5.13. Parabolic reflectors or parabolic antennas are high gain pencil beam microwave antennas. This is second part on these antennas. In this part, in this session, the focus is on various performance indicators and various efficiencies pertaining to these antennas. In addition, we also focus a substantial amount of time on Cassgrain antenna system. Let us begin the session with different performance indicators of paraboloid reflectors. Here are given 5 indicators. Power gain is given. It is nearly equal to 6 d by lambda. Lambda is wavelength, d is dia of the aperture. Then beam width, half power beam width is 70 over d lambda degrees. D lambda means d by lambda. The shape of the dish is given in the form of an expression. R is 2f by 1 plus cos theta. This is the property, mathematical expression for the property of the shape, reflector shape. Aperture distribution, how field varies over the aperture. E theta by E naught is 1 plus cos theta over 2. Then radiation pattern, E of phi, lambda over pi d to A1 pi d by lambda sin phi by sin phi. Capital D, small d, they are same. In the literature, sometimes capital D is used, sometimes small d is used. Both denote same thing, that is aperture dia. J is Bessel function. 1 is there, first order Bessel function. Phi is azimuthal angle. So this particular slide gives features, salient features of dish antennas. Next we move to a feature called aperture blockage efficiency. An obstacle in front of an antenna can alter the effective aperture illumination and distort the radiation pattern, which is called aperture blocking or shadowing. Many antenna designs, prime focus as well as Cassgrain, require structures to hold the feed and or sub-reflector in place. And these structures block part of the aperture. The efficiency due to blockage is defined as eta BL. Eta means efficiency, BL means blockage. It is unblocked aperture area to total aperture area square. It is nearly equal to 1 minus 2 aperture area blocked by total aperture area. This last one is for small ratio blocked to total area. Here it is extra. Don't consider this. Now the aperture blockage affects the beam shape in addition to aperture efficiency. The aperture blockage can be avoided or reduced by going for offset feed, but this may cause other unwanted effects which were listed in the previous treatment, that is in part 1 on parabolic reflectors. Feed spillover efficiency. The part of the energy radiated by feed and not intercepted by the dish amounts to a loss. This loss or spillover results in lowering of the overall efficiency and defeats the very purpose of uniform illumination. The feed spillover efficiency is defined as the ratio of the power intercepted by the reflector to the total radiated power by the primary radiator placed at the focus when it is functioning as a transmitting antenna. It is denoted by eta S. S stands for spillover. It is power intercepted by the reflector to total power radiated by the feed. This ratio is eta S. Power intercepted by the reflector can be calculated integral 0 to 2 pi 0 to psi by 2 u of theta phi sin theta d phi over integral 0 to 2 pi 0 to pi u of theta phi sin theta d phi. This is second denominator representing total power radiated by field. Here u is feed power pattern and psi is reflector half angular aperture. When the antenna is functioning in receiving mode, spillover sees the ground, resulting in increase of noise level and consequently noise temperature. Feed spillover can be avoided by under illuminating the dish so that there is no chance for the radiation to miss the edge and go to the sky or ground. Another efficiency we encounter in case of reflector antennas is illumination taper efficiency. A few points regarding this particular one. Maximum aperture efficiency is said to occur when the aperture is illuminated uniformly, but to avoid feed spillover, the dish is sometimes under illuminated at reflector edges, resulting in a tapered aperture distribution. Under illumination at the dish edge means that some of the collecting area goes unused. When the antenna is in receiving mode, the feed does not accept radiation from the edges of the under illuminated dish effectively. In either case, transmitting or receiving mode, under illumination of the reflector results in inefficient utilization of the reflector surface, resulting in reduction of the gain and effective aperture. This loss of efficiency due to non-uniform amplitude and phase illumination of the aperture plane is measured through illumination taper efficiency factor. Now, aperture efficiency. Aperture efficiency is a figure of merit, indicating how effectively the physical area of the antenna is utilized. For reflectors, aperture efficiency depends upon several factors. Most important ones are spillover, amplitude taper, phase distribution, polarization uniformity, blockage, and surface random errors. The efficiency can be increased using a reflector with a small angular aperture along with a feed having a radiation power pattern that is nearly proportional to secant theta by 2 power 4 over the angle subtended by the reflector. The latter requirement cannot be met without a large spillover loss. So a compromise between high aperture illumination efficiency and low spillover efficiency must be sought such that their product is maximized. So if we try to improve the efficiency in one direction, it is making a dent in the efficiency in other direction. The compromise has to be requires to be made depending upon the needs of the application on hand. Here is shown certain features, certain factors of aperture efficiency: illumination taper efficiency, aperture blockage efficiency, feed spillover efficiency. Aperture blockage efficiency by definition is unblocked aperture area to total aperture area square. Feed spillover efficiency is ratio of power intercepted by the reflector to total power radiated by feed. Illumination taper efficiency is 1 over A integral E dot ds whole square by integral E square ds. These are main factors: illumination, taper efficiency, blockage efficiency, spillover efficiency. These three are considered to be main factors determining aperture efficiency. Now we move to another aspect of reflector antennas. It is Cassgrain feed. It is considered to be the most versatile, highly efficient antenna system. We spent some time studying about this particular antenna system. Laurent Cassgrain, after whom this feed is named, he was born around 1629 and was a priest and professor by 1654. He may have been interested in acoustics, optics, mechanics. At the time of his death in September 1, 1693, he was working as a teacher, giving science classes to a high school-like institution. These are some points in which we may be interested regarding Laurent Cassgrain, after whom this particular antenna is named. The Cassgrain feed method employs shaped dual reflector surface. Two reflectors are there. Shaped reflector surfaces to achieve a better pattern control. The shape of the primary reflector is paraboloid, whereas that of the secondary reflector is hyperboloid. Primary is paraboloid, whereas secondary is hyperboloid. The focus of the paraboloid coincides with one of the foci of the hyperboloid. The rays emitted from the feed horn antenna are reflected from the hyperboloid mirror, and the main reflector then collimates the rays in the usual manner. Here is shown a simple block diagram of Cassgrain feed. A primary reflector is there, parabolic reflector. A secondary one is there, hyperboloidal reflector. And feed is here. At the vertex of primary reflector, horn feed, wave comes out of horn. It moves towards the secondary reflector. There it gets reflected towards the parabolic main reflector. From there, the wave gets collimated. It becomes a beam and moves towards the receiving antenna. To avoid the obstruction to some of the radiation from the main reflector, it requires the main reflector as large as possible and the horn be placed to the sub-reflector as close as possible. Larger the sub-reflector, nearer it can be to the main reflector, making the axial dimensions of the antenna assembly shorter, but aperture blocking becomes larger. Smaller the sub-reflector, farther it has to be to the main reflector, reducing the aperture blocking, but the axial dimensions of the antenna assembly becomes larger. These are some of the aspects, features pertaining to Cassgrain feed. In another method to reduce aperture blocking, a sub-reflector called trans-reflector, which is made of horizontal grating of wires, is used. The trans-reflector passes the vertically polarized wave with negligible attenuation but reflects a horizontally polarized wave radiated by the feed. It describes the functioning of trans-reflector. The plane of the reflected horizontally polarized wave gets rotated by twist reflectors at the surface of main dish, resulting in a vertical polarized wave. The reflected wave from the dish, now being a vertical polarized one, passes through the subreflector with a negligible attenuation. In this system, the aperture plane amplitude distribution is largely controlled by curvature of the subreflector, and phase distribution is controlled by largely the curvature of the main reflector. It is widely used in telescope design and monopulse tracking radar systems. It permits reduction in axial dimensions of the antenna and permits greater flexibility in the design of feed system. It eliminates the need for longer transmission lines. It is an advantage because the losses in longer lines degrade the sensitivity of the receiver. Some more points regarding Cassgrain feed. Cassgrain feed designs exhibit relatively large efficiencies. They range 65 to 80%. They also exhibit lower aperture blockage and lower spillover. Because of more uniform illumination of the main reflector and more uniform aperture distribution, improvement in gain is considerable. These are positive aspects, useful aspects, relative merits of Cassgrain feed. In addition, the side lobe radiation is low and has the capability for scanning and or broadening the beam by moving one of the reflecting surfaces. If desired, it can also be designed to have lower antenna noise temperature. This system first appeared in the 8th edition of 17th century French science journal about this reflector, where a secondary convex mirror is suspended above a primary concave mirror. This was around the time of the publication of construction of the first practical reflecting telescope, Isaac Newton's Newtonian reflector. On June 13, 1672, Christian Huygens wrote about the Cassgrain design and critiqued it harshly, maybe because Huygens felt Newton's design was being imperiled by this alternative. Gregorian reflector is similar to Cassgrain design except that the secondary reflector is a concave one in shape. This one is capable of providing an aperture efficiency of over 70%. Reflector antennas exhibit a pattern with the side lobes. What are the causes of the side lobes in the pattern? They are given here. 1. Aperture distribution is the prime factor for generating side lobes. Uniformity of the distribution gives rise to side lobes. 2. Aperture blocking caused by the primary source and its supporting stands can cause side lobes. Another factor for generating side lobes. 3. Diffraction from the feed, its supports. The effect due to this factor can be eliminated by going for offset feeds or horn reflector antenna. 4. Diffraction from the edges of the dish, which can be reduced by means of a serrated edge or rolled edge, with or without absorbing material or with reduced edge illumination. Fifth factor for side lobe generation is surface irregularities, like the deviations from the true paraboloidal shape should not exceed lambda by 16. When irregularities exceed this particular limit, usually it happens, it results in side lobe generation or creation. Sixth one, feed spillover. The radiation that is not covered by the reflector leads to the generation of side lobes. Seventh one, aberrations due to the finite size of the primary antenna may cause side lobes. It is because the source is supposed to be of a point-sized one, emitting equiphase waves. However, in practice, that type of sources never exists. Eighth one, uneven radiation of primary antenna towards the reflector. Remedial measures are measures that are capable of eliminating or reducing side lobes. What are those measures? Edge diffraction can be reduced by using a rolled edge. Offset feeds can reduce side lobes. These are some measures for reduction in side lobe level. Before going further, it is mentioned here that side lobes are indicators for wastage of power. Power at microwave frequencies is quite expensive, and it has to be used efficiently and effectively. Therefore, side lobes, which denote wastage, they require to be eliminated. Applications. Parabolic antennas are high gain antennas. Therefore, whenever we need higher gains, this can be used. Of course, at lower frequencies, their size becomes very large. So they are not suitable at low frequencies. Only at microwave frequencies, size becomes comfortable to work with. So at microwave frequencies, to have higher gains, these antennas are used, can be used. They are used for point-to-point communications in applications such as microwave relay links. They are also used in radio telescopes. They are used in radars. Radar is a system in which a narrow beam of radio waves is transmitted to detect objects like ships, airplanes, and guided missiles. With the advent of home satellite television receivers, parabolic antennas have become a common feature of landscapes of modern countries. With this, we come to an end to this session. Here, main focus is on performance indicators and efficiencies of parabolic reflectors along with the Cassgrain feed. At the end, we considered applications of these antennas too. Hope this session is useful to you. This is the second part, last part on parabolic reflector antennas. We meet again in another session with a new topic soon.